Historically, the family of catalysts you hear about today go back to the 1980s with a work by Union Carbide. And there we're talking about molybdenum vanadium oxide catalysts. And this worked very well, but the selectivity wasn't quite high enough, and the actual catalyst was fairly amorphous. Then in the 1990s, Mitsubishi introduced a new catalyst family, the so-called M1, M2 mixed metal oxide structures. And this had improved selectivity. Later on in the 2000s, Dr. Buttry of University of Delaware and co-workers elucidated the structure of the M1 catalyst. And a lot of advancements were being made, but we felt that still we weren't at the economic threshold. So this category of molybdenum vanadium niobium-based catalysts has had quite a bit of success in commercialization. With the incorporation of palladium by Sabic, they've converted ethane to acetic acid commercially. Incorporating tin, Asahi has a propane to acrylonitrile commercialization. Antimony addition has led to development stages of propane to acrylonitrile. And tellurium for propane to acrylic acid. Many companies have investigated that. The talk you hear about today, some of the patents shown here, the data and the patent examples are illustrated. And in our catalyst synthesis, we looked at different prep methods. We had a slurry method, a hydrothermal synthesis, microwave assisted. We looked at different families of catalysts, multiple components with promoters, and conducted characterization work. The slurry method looks rather involved. It has to be very carefully monitored in terms of pH, temperature. In the slurry phase, the polyoxymetallates form under a drying procedure and calcination. You can conduct these processes to favor the M1 structure. And then with post-treatment, one can remove the non-selective phases with oxalic acid extraction, and then we have a special grinding stage where we preferentially expose the active phases. Another methodology for getting the hydrothermal synthesis approach, you can prepare the M1 structure this way. And it's slightly different reagents, and temperatures are higher. If you replace the hydrothermal step, par bomb, with the microwave, you can reduce the synthesis time down to hours versus days and achieve the catalyst synthesis. The structures that are shown here, the preferential phase B is what we were after, the structure in the middle. And here, the preferred structure has a 5, 6, and 7 member ring arrangement. The top structure A, we call phase A, which is in the open literature called M2, is 6-member ring ordering and less preferred. So as you can see, the catalyst is needle-like. It can grow up to 200 nanometers in length. The cross-sectional area, the 001 plane, is on the order of 20 nanometers. And through our post-treatments, we could preferentially break along the AB plane to expose more of the selective sites. And in the TEM, this is what the structure will look like, and you can see the multiple oxidation states of the molybdenum, vanadium, and so forth. And this is the work that Doug Buttry and co-workers have elucidated. We ran conventional fixed bed reactor systems to do catalyst evaluations, and the gas hourly was 1,200. We could run higher. The data you'll see today is 1,200. And first we looked at the different prep methods that were outlined and found that in terms of a conversion selectivity curve, they performed in a similar fashion. The microwave catalyst was slightly less active, required slightly higher temperatures. And this is the performance curve. When we looked at different compositions, the inclusion of antimony was most preferred, giving us selectivities approaching 97%. And then we underwent a different optimization of the composition with the tellurium, varying it the stoichiometry, and saw that the various amounts of M1, M2 in the unknown phase were dependent on the tellurium. The conversion selectivity curve, the optimal tellurium level was coming in at 0.125, and it was also the most active composition. In a similar fashion, we optimized the niobium content, varying it from 0.17 to 0.21. It was found that too high a level of niobium led to the amorphous phase. And the conversion selectivity curve, we were focusing in on optimal composition of 0.19. And again, this was the most active. So how does this compare to the commercial cracking of ethane to ethylene, which is non-catalytic endothermic? At 70% conversion, we found with this 5-component catalyst system of niobium, roughly about 15% higher in selectivity. Then further investigations were done. I don't really have enough time to show everything, but we were able to increase the ethane feed content for higher productivity up to 35%. We were able to use the diluent of steam versus nitrogen, which would be better for plant operations and also heat removal, and raise the pressure up to 30 psig. And under these conditions, there was good catalyst life on the order of months. So really the next step would be to look at it more from a process scale-up viewpoint. And surprisingly, the catalyst, our concern was if you ever had a system upset, it might undergo phase changes. But we were able to oxygen starve it for roughly 2 hours by raising the operating temperature up to 390 degrees C. Come back, regenerate the catalyst with air, and go back to the operating conditions again and not suffer too much of a loss in selectivity on the order of 2 to 3 points. As I mentioned earlier, we felt it would be best to have a ppm level of oxygen in the effluent to maintain catalyst stability, and patented finishing catalysts, as we called them, to remove the residual oxygen in the effluent. The other concern was that there could be up to possibly 100 ppm acetylene in the product slate. So to make this a safer environment for downstream processing, we incorporated very low levels of platinum to finish off the acetylene, convert it to CO2. And we also looked at the tolerance of the ethane feed containing propane, and saw no negative effect of running a feed of 6% propane and ethane in terms of selectivity. So this short program in research, we felt we had achieved a composition and performance level that was adequate to be competitive with the ethane cracking, and tried to address what we thought were key challenges and provide solutions. But as you can see, this type of approach can be fairly time-consuming. And how can we be more logical about how we do our problem solving? And so, as you can see, going from the bench all the way up to manufacturing, this is an illustration of maleic anhydride process, but it's a multi-scale, usually very complex, very dynamic, a lot of interactions. The catalyst is almost a living entity. It's very responsive to its working environment. And for problem solving, really you're looking at usually a bulk crystalline structure. It's polycrystalline. The surface will be very different from the bulk. Usually you're talking about defects, amorphous phases, different reaction conditions. It's usually a very complex reaction system, as we just spoke about, with a multi-component mixed metal oxide. And traditionally, people solve the problem looking at it maybe in 3 different ways. You know, you worry about making the catalyst, and then you have to be concerned about characterizing it, and then relating it to the reaction kinetics.